In this lesson, I'll show you how to solve a rotational problem involving kinematics. The question reads, consider a space station in the form of a donut with a rectangular cross-section connected by spokes to a central axis. The floor is the inside of the outer wall. For question A, how fast would a 300-meter radius station have to rotate to duplicate the acceleration due to gravity on the surface of the Earth? The word duplicate here meaning the same. To solve this type of problem, we need to keep in mind two important formulas. The very first one is the acceleration associated with rotational motion, or centripetal acceleration. To calculate centripetal acceleration, we write down acceleration is equal to the velocity raised to the power of 2 over r. The second relationship is angular velocity, which we represent using the Greek letter omega, and that is equal to the velocity over the radius. And we use this formula only when dealing with angular motion. So what I want to do is use the information to solve for omega. I'll solve for v here and substitute that into v found in this formula. Then we can find out what angular velocity is equal to. So to solve for v is not hard to do. You just multiply both sides of this equation by r, and you should end up with a times r is equal to v squared. And then you square root both sides, where you end up with the square root of a times r is equal to v. Like I said, I'm going to take this now and put it right into v. So I have omega is equal to the square root of a times r over r. And from here, all I have to do is substitute my values, 300 and 9.8 meters per second squared, in for a. So here's what happens. The square root of 9.8 meters per second squared times the radius of 300 meters over 300 meters. The square root of 9.8 times 300 divided by 300. And we end up with 0.181 rounded. 0.181, and the units will be per second. Now you may also, instead of writing per second, and since we're dealing with angular velocity, you can write down radians per second. Writing it this way will actually come in handy when converting radians per second into revolutions per minute. And that's what we'll do next to finalize the answer for A. Now we're only doing this, we're only converting to revolutions per minute so that it's more understandable to the reader. So if I want to convert radians and seconds to revolutions per minute, I need to know the relationship between radians and revolutions. There are 2 pi radians per every 1 revolution. And there are 60 seconds per every 1 minute. So using what we know, I'll take this value of 0.181 radians per second, and I'll multiply it by 60 seconds at the top per 1 minute at the bottom. The seconds unit cancels out. And then I'll multiply this by the second relationship, where I have 2 pi radians at the bottom per 1 revolution. So this unit and that unit cancel out. And we can now go ahead and calculate the value on our screen times 60, so all the numbers in the numerator position, divided by 2 times pi. And we get 1.725, or simply 1.73 revolutions per every 1 minute. So this space station would have to revolve that many times per minute in order to have the same acceleration due to gravity that you would find on Earth. And in part B, we're asked if someone of weight 800 newtons living in the space station were to move 1/2 the radius in towards the axis of rotation, what would be his or her weight at this radius? Now to be successful here, you need to remember that weight is equal to one's mass times the acceleration due to gravity. We are told that the weight of this person on Earth is 800 newtons. And the acceleration due to gravity on Earth is 9.8. So the person's mass can be found by taking 800 divided by 9.8. And of course, you should be including units here. So this should be 800 newtons and 9.8 meters per second squared. Dividing these two values out, you get a mass, the mass of the person. So let's go ahead and do that. Just for simplicity's sake, write it down. 81.632. 81.632 kilograms. Now, we want to find the weight in the space station. So again, weight is equal to mass times acceleration. And because we are dealing with radial acceleration or centripetal acceleration, I'll change this a with what I had it before as v squared per r. And rather than using velocity, since we're dealing with angular motion here, I'll use the relationship with angular velocity. Remember, omega is equal to v per r. Solving for v, I have omega times r is equal to v. Now I'm close to substituting values into this formula, but let me just replace this v with the following. So mass times omega times r raised to the power of 2 per r. That's equal to the person's weight. Now their mass, as we said earlier, is 81.632. The value for the angular velocity we found earlier to be 0.181. And the radius is cut in half, right? We're told that it's half the radius as before, so 150 raised to the power of 2 over 150. So using our calculator, we have 81.632 times 0.181 times 150 raised to the power of 2. Then we divide this by 150, and we get around 401 newtons. 401 newtons would be the weight of the person 1/2 the radius towards the axis of rotation on this space station. And there you have it. That's how to solve rotational problems involving kinematics.